Okay, welcome back. This is 7.3 on partial fractions. So let's take a look. Get my pen going. 7.3 partial fractions. Essentially what this is just the reverse direction of finding a common denominator and combining two fractions. Okay, so before, you probably had these kind of problems, 1/3 plus, I don't know, 1/2. To combine them, you need a common denominator, so multiply top and bottom by 2, over here by 3, sorry. So you'd end up with 2/6 plus 3/6, and finally you would have 5/6. Okay, so this is like the before. And then now you want to go in the other direction. So they give you 5/6, and they want you to split it up. And the way you can kind of think about this is, well, we can factor 6 into 2 times 3, and then it's going to be something over 2 plus something over 3. And we need this to work out, so I need 5/6 to equal a over 2 plus b all over 3. How are we going to figure this out? I'm going to multiply everything by 6. 5 is 3a plus, I guess, 2b. And then, I don't know, 1 and 1, right? So a looks like it could be 1. Or, a equal 1. And you get 5 equals 3 plus 2b. So 2b equals 2, and b equals 1. So this must be 1/2 plus 1/3. Okay, so it's this process of going in reverse that we need to talk about. And it's crazy that we waited so long to introduce it. I mean, it seems like we've spent years teaching you how to do this process. Now we want to do this other process. Okay? And a lot of things in math are like this. So like it's easy in one direction, and then you try to do it in the other direction. It's impossible. It's like it's easy to crack an egg and fry it in a frying pan. It's kind of hard to take an egg in a frying pan and turn it back into the original egg, uncrack it, right? So a lot of things in math are like that. Even your cell phone security, the cryptology that you use to send messages back and forth is based off of this kind of, it's easy to go one way but hard to go the other way type idea. Okay, so anyways, without further ado, we want to start doing this process, and not only do it with just arithmetic, we need to do it in variable land here now as well. So recall what that process looked like then. So we would want to maybe combine these two fractions into one fraction, right? So what do we have to do? It was like we need to multiply top and bottom of this first guy by x plus 2. So here is x plus 2 on top and bottom, x plus 2. And this guy over here, we need to multiply top and bottom by x minus 4. Right? And then we would have our numerators over the common denominator. So we would have 3x plus 6 minus 2x plus 8. You distribute all over our new common denominator of x plus 2 times x minus 4. And then we would have, I guess, 3x minus 2x is 1x, and plus 8 plus 6 is 14. And we end up with x plus 14 all over x plus 2 times x minus 4. Okay, so before we had this process, now we want to go in the reverse direction. Okay, so we'll have x plus 14 all over x plus 2 times x minus 4. And the first step is to just build a fraction for every factor you have in the denominator. Okay? So factors, the things you're multiplying together. So there's one factor, there's two factors. So we're going to build two fractions. Okay? So our first fraction will have the x plus 2 in the bottom. Our second fraction will have the x minus 4 in the bottom. And then we're just going to put a and b in the top. And then we have two different methods for solving this final form here. and I have to teach those to you. Okay, but first we just need to know how to do these setups, because we need to be able to do it for basically any rational function. So also we need to be able to do it for things like x plus 4 all over x plus 2 squared times 2x plus 4 times x squared, I don't know, plus 3. I need to be able to set these up, and they're a little different than this problem right here. Okay? So just setting it up is half the battle, and that's where we want to start. Okay, so first just setting it up, and then we'll work about how do I figure out what is A, what is B. Okay. So first is the setup, and there's 4 different types of setups based on the denominator. Okay. So the first type of setup is when you have just a bunch of linear factors in your denominator. So basically primes in your denominator. So let's look at some examples, like number 16. Here we have x all over x squared plus 2x minus 3. So you want to factor the denominator if possible. So it'll be x plus 3 times x minus 1. And then what you do is just plug, you're going to have a fraction for each factor in the denominator. So your first fraction is over x plus 3 plus, and the second fraction over x minus 1. And then the numerators, you're just going to put some variables. We use A, B, C, D, the letters of the alphabet. Okay, so that's the setup. We don't care too much yet about solving. Let's look at another one. Number 10. We have 1 all over x squared minus x. Okay, so first factor it. I got x times x minus 1. And then here I have 2 factors, this guy and this guy. Okay, so I need 2 fractions. I need 1 for the x, and then 1 for the x minus 1. And on the top, you just put the variables. Okay. Let's look at another one. This one is already factored, number 9. So we have x all over x. Let's make it a little more challenging. So I'll make it, it's like number 9. Okay, so what do I do here? How many fractions am I going to need? You need 1 fraction for every factor. Okay, so you need 3 fractions. So I'll have x minus 3, x minus 2, x plus 4. And then you just go A, B, C. Okay, so this is our first type of setup. Linear factors are basically anything like x plus 3, 2x plus 1, just x. Okay, those things are all linear factors. And when you see that, you just give it a fraction and put a variable up top. Okay, so the next kind of setup is when you have repeated factors, repeated linear factors. Okay. So for example, number 21, we have 6x minus 11 all over x minus 1 squared. In other words, you have x minus 1 times x minus 1 in the denominator. So what you're going to do here is basically you'll have a fraction for each factor of x minus 1, but you increase the exponents on the x minus 1 for every fraction until you get to the exponent in the denominator. Okay, so let's see another one. So how many fractions do we need? We need 4, right? So you need 1 is x plus 3, and then you increase the exponent, so you have x plus 3 squared, and then you increase the exponent, you get x plus 3 to the 3rd, and then you increase the exponent, you get x plus 3 to the 4th. Okay, and up top, you get A, B, C, D. Let's look at another one. So this one is a mixture of repeated and non-repeated. You just treat the non-repeated like we did before. So here, The x plus 1 is non-repeated, so I need a fraction for that guy. And then the repeated ones, so I need 2 fractions for that. The x minus 1, x minus 1 squared, and then that would be b, and that would be c, and that's it. Okay, so hopefully that's kind of done. The next type then is the irreducible quadratic factors. So if you're in the real numbers, you could take any polynomial, like p of x equals a sub n x to the n plus a sub n minus 1, x to the n minus 1, plus dot 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 plus a sub 1x plus a sub 0. You could take anything like that and factor it into a bunch of factors where the degrees of the factors are going to be linear and quadratics. So you'll have x minus c1, x minus c2, but some of these won't be factorable. So you'll have something like x squared plus, I don't know, bx plus c3, maybe b1, I don't know. So it's these guys that you have to watch out for. And we see these in math, whenever you try to factor something like, so try the factor x squared plus x plus 1 versus factoring x squared plus 4x plus 4, right? So you're trying to factor this thing, this guy is not an irreducible quadratic, okay? So this is not irreducible, because you could factor it in x plus 2 times x plus 2. So not irreducible, but this guy is irreducible because there's no way to kind of factor it. It has to be plus plus, it would have to be 1, 1, and there's just no way to do that in the real numbers. If you look at the discriminant, x equals -1 plus or minus the square root of 1 squared minus 4 times a times c. The discriminant is negative, okay, all over 2a. This is less than 0, which implies it has no real solutions. You're not going to be able to factor it in the real numbers. No real solutions. Okay. So this guy then is what I'm talking about with this irreducible quadratic. Okay. So you could take any polynomial and break it into a bunch of linear and irreducible quadratic factors. Okay. So the question now is, when your denominator has an irreducible quadratic, what are you going to do in those cases? So let's take a look. Here I have x cubed. The numerator doesn't really matter at this point. It will when we go to solve for the variables in the top. Okay. Oops. This isn't 37. I want to do 31. I'm sorry. 31. My pen starts working. That would be great. And let's get rid of this. Wrong problem. Sorry. So 31 is 5x squared plus 6x plus 3 all over x plus 1 times x squared plus 2x plus 2. Okay. So this first guy is your usual linear factor. So that's just business as usual. Give it a fraction, x plus 1, put a variable on top. Okay. The second guy, what about that guy? Can you factor it, right? Has to be x plus and x plus. Has to be 2 and 1. But if you FOIL that out, you'll get 3x in the middle. So there's no way to factor it. It's an irreducible quadratic. So what do? You're going to give it its own fraction, so you put it in its denominator, and then the numerator, you're going to put a linear factor. Okay, so instead of just writing a, which would be just a constant, you're going to write bx plus c. Okay, and that's the setup. Okay, let's try another. So here we have x plus 4 all over a repeated linear times an irreducible quadratic. So again, x squared plus 4, you cannot factor that. You could try, but you'd end up with a middle term from the inner and outer. Okay, so it's irreducible. Okay, so for the x squared factor, that's repeated linear, it's x times x. You need two fractions, one for x and then one for x squared. And then the irreducible quadratic gets its own fraction. And in its numerator, we put something like blah x plus blah, right? So in this case, cx plus d. We just keep the alphabet going. Okay. Okay, the last type then, if you look, we had linear factors, repeated linear factors, irreducible quadratics. The last kind is the repeated irreducible quadratics. Okay, so repeated irreducible quadratics. And let's take a look. So 37, x cubed plus x squared plus 2 all over x squared plus 2 squared. Okay. So this thing in here cannot be factored, x squared plus 2. You can always factor something like x squared minus 2, right? Or x squared minus 4. If it's a difference of squares, you can factor that. That would be x minus 2 times x plus 2. Or even if you had x squared minus 2. That would end up being, excuse me, I'm sorry. That would end up being x minus root 2 times x plus root 2. But when you get something like x squared plus 4 or x squared plus 2, those are irreducible quadratics. Okay, they're considered prime. Like prime numbers, you can't factor a prime number. These are prime polynomials. Cubics, you can always break them down, right? A polynomial with third degree, fourth degree, fifth degree, you can always break those down into products of linear and then irreducible quadratics. Okay, so anyways, here, this guy is an irreducible quadratic and it's repeated. Okay, so how do I deal with that? Well, you're going to give a fraction for every repeat. Okay? And let's make it worse, right? Let's make this x cubed. So if it's x cubed, you need a third one. So you need 3 fractions. And again, what you do is just keep incrementing the exponent until you get to the exponent in the denominator. Okay. And then the numerators, you have to put blah x plus blahs. Make sure you go A, B, C, D, E, F, whatever. And then we would implement our methods to solve that. Okay. Okay, one more. Let's get one more example. This is 41. So 4x squared plus 3x plus 14 all over x cubed minus 8. Okay, x cubed minus 8, we can factor that. That's a difference of cubes. So we'll get x minus 2, same, opposite, always positive. And then x squared, and then 2x, and then 4. Okay, the first factor is linear, and then this factor turns out to be irreducible quadratic. You can't go any further. So we need 2 fractions, a all over x minus 2 plus this other guy, irreducible. So in the numerator we put bx plus c. Okay, and that's it. Okay, so we know how to set them up. Now we need to worry about solving them. And again, there's 2 methods. There's this equating coefficient method. And then there's going to be a substitution method. Okay. so the equating coefficient method is kind of an algebraic method, and it's like this, folks. If you have 3x cubed, or 3x cubed plus 2x minus 1, and then on the other side you have a plus b x cubed plus c x squared plus, I don't know, b plus c x plus e. What you can do is equate the coefficients on both sides. Okay, so over on the left you have 3x cubed plus 0x squares plus 2x minus 1. On the right you have a plus b x cubed plus c x squared plus b plus c x plus e. And this algebraic rule says that the coefficient on the left of x cubed is equal to the coefficient on the right of x cubed. So we can set those equal to each other, and we'll have some equations. So first off, 3 is equal to a plus b. Okay. And then the second equation, we have 0 must be equal to c. So 0 is equal to c. I'll erase that. Zero is equal to c. And then the third part there, we have 2 equal to b plus c. Okay. So 2 equals b plus c. And then the last part we have negative 1 is equal to e. Okay. And then we could solve for a, b, c, and I guess I should have used d, but I didn't, sorry. A, B, C, and E, right? So E is already, we already know E is negative 1. B plus C right here is 2. We know C is 0, so we can plug that into here and solve for B. So 2 equals B plus 0, which is B, so B is 2. Then I could take the 2 and substitute it in right here and get A. So 3 equals A plus 2, so A must equal 1. And that's the process you use. Okay, so it's like you equate coefficients and you build what is essentially a system of equations, and then you solve that system using the addition method, or what I did was the substitution method. Okay, okay, so let's try this on one of the problems, and you'll see that this is going to give you a lot of practice with algebra. Okay, so 27. I have x squared all over x minus 1 squared plus x plus, or times x plus 1. So the first step is just the setup. Okay. So I need 3 fractions, one for the x minus 1, and then it's repeated, so I go x minus 1 squared, and then I need 1 for the x plus 1. They're all linear, so they just get a, b, and c. And then we need to figure out what a, b, and c are. So what I do first is multiply everything by these by the denominator on the left-hand side. So I'm going to multiply x minus 1 squared times x plus 1 over here. And you do the same thing on the other side. On the left, you should just be left with the numerator, and then on the right, you have to distribute all 3. So for the first term, it'll be the x minus 1, one factor of x minus 1 will cancel, leaving you with x minus 1 to the first power times x plus 1 times a, plus, when you distribute to the second term, the x minus 1 squares cancel, and you'll just have x plus 1 times b, plus, and the last term, the x plus 1's cancel, leaving you with x minus 1 squared, which is, you can put the c in the front or the back, it doesn't matter. Okay. Now what you do is FOIL. FOIL out the x minus 1, x plus 1, that'll be x squared minus x plus x is 0, and then minus 1 times a, plus the x plus 1 times b, and then plus x minus 1 squared is x squared minus 2x plus 1 times the c. Then you're going to distribute the a, the b, and the c. Okay, so we'll have ax squared. You want to put variables first. But the order of the terms will always go constant, then letter, then variable. Okay. For instance, here, when you're distributing the c, you're going to have negative 2c x squared. Okay, that's generally how you'll order the guys. Okay, so anyways, ax squared minus a plus bx plus b plus cx squared minus 2cx plus c. Then we want to start grouping like terms together. Okay, so on the left I have x squared, on the right I have ax squared plus cx squared. And then I want the x's, so I have plus bx minus 2cx, and then I want the constants, okay? Minus a plus b plus c. Now it's a problem like I introduced the section with. It's one of these problems where you equate the coefficients on both sides. Okay? So to make that happen, I'm going to have to factor out the x squared, factor out the x, and then I just have the constant. On the left-hand side, you can pretend it's 1 times x squared plus 0 times x plus 0. So on the right side, factoring out the x squared, you have a plus c times x squared plus b minus 2c times x, and then plus the negative a plus b plus c for the constant. And then you build your system of equations. So the coefficient of x squared is 1 on the left. It's a plus c on the right. So your first equation will be a plus c equals 1. Or 1 equals a plus c, whichever way you want it. The second equation is going to be 0 equals b minus 2c. Or if you'd rather, b minus 2c equals 0. And then your last equation will be 0 equals negative a plus b plus c. Okay, so, I'll just write it, negative a plus b plus c equals 0. And then you solve this system. Okay. So I don't know how I want to proceed. I guess I'll do a substitution type method. You can solve for c in this equation, this first equation. I don't know. What's the most direct way? Okay, so yeah, sure. Let's solve for c here. So c equals 1 minus a, and then I'm going to substitute that into this equation. So I'll get b minus 2 times 1 minus a equals 0. Well, maybe no, that's not a good way to go. Sorry. So there's not too much methodology for the way I just kind of do substitutions and hope something works out. So the second equation, you could solve for b really easily. B is 2c. Okay, and then you could plug that into here, and you get negative a plus 2c plus c equals 0. So you get negative a plus 3c equals 0. And then you could solve for, I guess, a. So you get a equals 3c. And then you could sub that in back over here and solve for c. So a is 3c plus c equals 1. So you get 4c is 1, and then you get c is 1/4. And then you just start back subbing. So if you plug c into there, you get b equals 2 times 1/4. So b will be 1/2. And then if you plug c into here, you'll get a equals 3 times 1/4. So A will equal 3/4. Okay. And then finally, you can rebuild your equation. At the end of the day, what did we begin with? Something like x squared all over x minus 1 squared times x plus 1. And then you're just filling in the numerators, right? So you could write it, x minus 1 squared, and then it was x plus 1. Make sure you get it in the same order as before. This one, yeah. Then A is 3/4, B is 1/2, and C is 1/4. And that's it. You've done it. So it's not a simple process by any means. The book will maybe rewrite this as 3 all over 4 times x minus 1 plus 1 all over 2 times x minus 1 squared plus 1 all over 4 times x plus 1. That gets rid of the complex fractions, the 1 over 2 over 3 over 5 over, no. Okay, so you can do that if you wish. Okay. So that's one problem. You can see they're nasty. Let's look at the other method, the substitution method, which is much easier, but unfortunately, it doesn't always work. Okay, so we'll look at the same problem, and you'll see it's much quicker. X minus 1 squared times x plus 1 equals A all over x minus 1 plus B all over x minus 1 squared plus C all over x plus 1. Okay. The first step is the same. You multiply to get rid of the denominators. And now is where it changes. So look, if you plugged in 1, x equals 1, you're going to have a lot of cancellations, right? So 1 squared is 1. On the right-hand side, a times 1 minus 1 times 1 plus 1 is the same as a times 0 times 2. Anything times 0 just turns into 0. So the first term will be 0. And then if you plug in 1 for the second term, you'll get b times 1 plus 1, which is b times 2, which is 2b. And then if you plug 1 into the third term, you get c times 0, which is 0. So you automatically get b as 1/2. And then try x is negative 1. Okay. So on the left, you're going to get 1. On the right, negative 1 squared is 1. On the right, a times negative 1 minus 1 times negative 1 plus 1. Again, now you're going to get a 0. This will just be 0. And then b times negative 1 plus 1 is 0. And then c times negative 1 minus 1 is negative 2. Negative 2 squared is 4. Okay, so you get c as 1/4. Then you can basically use any number you want to sub in because you have b and c, and all you have to do is solve for a. So try x is 0, right? So 0 is a times negative 1 times positive 1 is negative 1 plus b, which is 1/2 times 1. 0 plus 1 is 1. Plus c, which is 1/4 times 0 minus 1, which is negative 1 squared. Negative 1 squared is 1, so it would just be 1/4. And then solve for a. Common denominator. And we got our answers. Okay. Just like last time. So the partial fraction, and they call it a partial fraction decomposition, would be 3/4 all over x minus 1. It's just what we got before, plus 1/2 times x minus 1 squared, plus 1/4 all over x plus 1. Okay. Okay. The only drawback, and the reason why, I mean, there's several reasons why we don't just teach this method. So one reason is that it doesn't always work. Okay. You may argue, well, I can use imaginary numbers and I can figure it out, but still, even then, it seems like it doesn't always work for me. Okay, I've tried that. So that's one reason. It ain't always going to work. The second reason is this technique that we're using with equating coefficients is used a lot later in mathematics. If you're going to continue learning math, it would become an important tool to have in your toolkit. So we want to make sure for those guys that are going forth, we'll have it. Okay. On my test, I'll probably just have the easy ones where you can always do a substitution. Okay. But if you're going to go on and keep taking like Calc 1, Calc 2, Calc 3, Calc whatever, you're going to probably need that coefficient method as well. Okay, so just keep that in mind. Okay, so let's try one more. In this case, we want some irreducible factors, right? Well, we haven't really seen that yet. And these things force you to have to use the coefficient method. Okay, so this has an irreducible repeated quadratic factor in the denominator, so I'm going to need two fractions, and then x squared plus 2 squared. Across the top, ax plus b, and then cx plus d. You have to use different variables for every term. We have to use the coefficient method, so we're going to multiply both sides by the denominator, x squared plus 2 squared. And on the left, we'll have x cubed plus x squared plus 2. On the right, ax plus b. For this first factor, only one of the factors of x squared plus 2 will cancel, so you'll have ax plus b times x squared plus 2. And then the second one, both factors will cancel, so you just be left with cx plus d. Okay. On the left, we have x cubed plus x squared plus 2. On the right, I need to FOIL. Ax cubed plus outer is an inner. The inner is bx squared. The outer is plus 2ax plus 2b, and then plus cx plus d. Then we want to start collecting the like terms together. On the left, I have 1x cubed, so I start getting the coefficients I'm going to need. 1x squared, 0 x's, 2. And on the right, I'm going to collect the x cubes together. There's only one of those. And then the x squares. There's only one of those. And then the x's. There's 2 of those. Let's go ahead and factor out the x. So we have 2a plus cx. And then the constant part, the 2b plus d. Okay. Now we can build our system. So the coefficient of x cubed on the left is 1. On the right, it's a. So we have a equals 1 already. Sometimes these are quick, but other times. Then we have b is 1. And then 0 must be 2a plus c. And then we have 2 is 2b plus d. Okay. So first I'm going to solve for c by I could plug in a and eliminate that variable. 2 times 1 plus c is 0. So 2 plus c is 0. So c is negative 2. And then I can plug the b into here and get d. So 2 equals 2 times 1 plus d. So 2 equals 2 plus d, and d equals 0. And that's fine to have one of those variables equaling 0. Okay, that happens. So then ultimately we go and plug those numbers back into the original decomposition, and we get x squared, x cubed plus x squared plus 2 all over x squared plus 2 squared. That'll equal our ax plus b all over the x squared plus 2 plus cx plus d all over the x squared plus 2 squared. And what is that for us? That'll be 1x plus b, which is 1, all over x squared plus 2, plus, negative 2x plus 0 all over x squared plus 2 squared. Okay, so there it is. More of the story, I guess. Doing it in one direction is kind of easy at this point. That other direction is a nightmare. Okay, but it is necessary. We'll need it later on in the math universe. And it's good practice for algebra, so you get plenty of algebra practice. Okay, so we'll leave it at there, and we'll see you next time. Thanks for watching.